Section 3.3, log rules, or log laws. Here's the first one. This is called the change of base formula. It's not nearly as important anymore because a lot of our graphing calculators have a log button on them that let you use whatever base you want. But you better believe in the next forthcoming quizzes, you're not going to have that graphing calculator available. I'll probably have a cheapy deepy, which only has a common log or natural log button. So how in the world are you supposed to do something like, I don't know, log base, give me a number, 13 of 52. There we go. Okay, it's going to be 1 point something, right? Because 13 squared is 169. 13 first is only 13. So it's going to be 1 point something, but I have no idea. Okay? 1 point, some nasty, transcendental, irrational number. Well, this formula, this change of base formula right here, allows you to rewrite that logarithm as a new logarithm of a different base. So let's suppose I have a calculator that all it has on it is a log base 7 button. So I can say, what is the log base 7 of 52 divided by the log base 7 of 13? That's how the change of base formula works. Whatever your original input was is now the input of your new log base in the numerator. Whatever your old base was is now the input of your new log base in the denominator. So, first of all, let's actually calculate what is the log base 13 of 52. 1.540476309. What is the log base 7 of 52 divided by the log base 7 of 13? Hey, same thing. Right? Now, typically we don't use this to rewrite our logarithms in terms of a log base 7. We typically use this formula to rewrite our logs in terms of what? Natural log or common log, log base 10, because those are the two logs you actually have buttons for on all of your calculators. Now, I think it's silly. I think it's really ridiculous that our graphing calculator, on the very actual buttons, has a button for common log and a button for natural log. Apparently, both of those are used so much that they got top priority. They're not even a second option for a button. They're the first option for those buttons, which is kind of weird because they actually literally ran out of buttons when they made the TI-84. They had the TI-83, and it was great. And then all of a sudden, somebody was like, you know what, we should make this new feature on the calculator called finance. But we don't have any more room to put the finance button. So I had to put it under apps. If you go to apps, one of the first things there should be finance. You cannot delete that. That's hard-coded in your calculator. It's the only app that can't be deleted. And they literally put it there because they ran out of buttons. I say, get rid of LOG. You don't need it. Just make everything natural log. You only need one log button. Put finance. Give it its own button. Maybe make it the second option for, I don't know, what seems not very important. Number 7. Why not? Or just get rid of the number 7. Forget finance its own button. Get rid of 7. You don't need it. Just write 6 plus 1 every time. 8 minus 1. Just be creative. Whatever you need. I always like the calculators that never had the negative button, so you literally had to type 0 minus and then your number whenever you wanted a negative. Yeah, why do you need a question mark? Why does it get its own alpha? Well, I'll tell you, how else can you use a calculator to ask people to home code?
Oh, yeah.
That's what I did.
I got this cool math problem. Check it out.
Aww. They first have to decipher it out of binary. Okay. So, we typically use this to rewrite things in terms of natural log. The biggest thing you're going to hear me emphasize as we learn these log rules is not just knowing these rules, but knowing what you're not allowed to do. Because trust me, there are so many things when it comes to logarithms that I could present to you, and I will find most of my students coming up with an answer, and the reality is these things don't simplify at all. Okay? So we'll talk about that. But do you remember the change of base formula? Remember that? So you're going to want to know that as we start solving log equations tomorrow. If I want the answer as a decimal, meaning you have to use your calculator, but you're not going to have your graphing calculator, you'll have a cheapy deepy, make sure you can find out what the log base 13 and 52 is, only being allowed to type the natural log button. Cool? All right. Then we also have these log rules. Okay? The product property and the quotient property, those are basically the same rule, to be honest. And then the power property. Actually, the quotient property is just a combination of the power property and product property, and I'll explain that. But the product property basically says if you have a log of a product, so a multiplication of things being inputted into a logarithm, you can do what we call expanding. You can expand that into the sum of two separate logarithms, one for each factor. And you can use this rule either way. Maybe you have two logs being added and they have to be the same base, and you choose to condense them together. We call this expanding and condensing. Division is a similar property, except for it becomes a subtraction of two logs. And then there's the power property. If you have a power being inputted into a logarithm, you can take the exponent of that power and bring it out in front, and it becomes a multiple of that logarithm. That is a huge, huge property when it comes to solving exponential equations. That allows me to take numbers and unknowns that are in exponents and bring them down to our base level so I can easily get them by themselves using addition, subtraction, multiplication, division, and all that fun stuff. Do you remember these properties from Algebra 2? Or do you remember having learned them? They'll come back to you pretty quick. I would like to prove some of them, a formal proof. I love proofs. I like puzzles. Who said I hate proofs? Gary. Okay. So I want to prove this one. I want to prove that the log base A of capital A times B is equal to the log base A of capital A plus the log base A of capital B. Okay? So that's the product property. Let's prove that. So here's how this proof begins. Let's create two new variables. Let's let x equal the log base A of A, and let's let y equal the log base A of B. Okay? Now those are both log expressions. Can't every log expression be translated into an equivalent exponential expression? So can't this log expression be translated into a raised to the x power equals capital A? Agreed? And a raised to the y power equals capital B? Okay. So now let's now take a times b. Well, according to these statements up here, using simple substitution, isn't that the same thing as saying a to the x times a to the y? And how do you multiply powers that have the same base? So that becomes a to the x plus y. So here's what we have. A times b equals lowercase a to the x plus y. Agreed? Well, is this right now a logarithmic expression or an exponential expression? Exponential. Let's now translate it to its equivalent logarithmic expression. That would be the log base a of a times b equals x plus y. Agreed. But let's substitute again. What is x actually the same as? Log base A of capital A. And what is y actually the same as? Log base A of capital B. And that's the end of our proof. Look at that proof. That is a beautiful, formal...
That's a square, clearly.
I don't know. I was watching a proof on YouTube once, and they wrote a square at the end when they were done. True story. I've actually seen that before, but yeah. It's common when you finish a proof and like, boom, done, draw a little square. Mathematicians have all kinds of shorthand. Like I should have put a triangle of dots right here, upside down triangle here. That means therefore, this means hence. This means if then, if this then this. Square means done. Eat it. Now isn't that a beautiful proof? None of that two-column crap. That's a gorgeous proof right there. Okay? So why is it that a log of a product becomes a sum of two logs? It is because when you multiply powers of the same base, you do what with the exponents? What's the exponent rule? When you multiply powers of the same base, you add the exponents. That's all this log rule is saying. When I multiply two powers of the same base, I add their exponents. Because aren't the outputs of logarithms exponents? That's all this log rule is stating. The other one that we can prove is the power. So let's prove that the log base A of capital A to the n is equal to n times the log base A of capital A. Okay, let's start by letting x equal the log base A of A. Therefore, A equals A to the x. Agreed. Yep. So hence, A to the n will actually equal A to the x to the n. And how do you raise a power to a power? You multiply. So this just becomes A to the nx. So I have capital A to the n equals lowercase a to the nx. Let's rewrite this as its equivalent log expression. Log base lowercase a of capital A to the n equals nx. And what was x to begin with? Log base a of capital A. Boom. So why does this log rule that allows me to bring an exponent from inside the log down as a constant multiple outside? It all boils down to that exponent rule that when you raise a power to a power, you multiply the exponents. When you raise a power to a power, you multiply the two exponents, n and then log base a of a, which is the exponent of a. Okay? Then, the division rule isn't division the same thing as multiplying? But so is a divided by b the same thing as a times b to the negative first? Where only b is being raised to the negative first. So can't I use my product rule and call this the log base a of capital A plus the log base a of capital B to the negative first? But then I have that power rule that lets me bring that negative 1 down. And hey, there you go. So we just proved all three of these properties. Right? Heck, while we're at it, how about we prove the change of base formula as well? Sound good? This one won't be a formal proof. This will be pretty informal. Let's take the equation 3 to the x equals 10. What power of 3 gives me 10? 2 point something, right? It's a good guess. 2 point something. Any idea what? Well, isn't this, can I just say the log base 3 of 10 is going to equal x? Does everybody agree that log base 3 of 10 is the solution to this equation? Yes or no? Yes. Now, I could have actually solved this equation a different way. I could have taken the natural log of both sides. I have this new power rule that tells me I can do what with this x? Put it out front. And then what can I do to get x by itself? Divide by natural log 3. So apparently, natural log 10 divided by natural log 3 is the same thing as the log base 3 of 10.
And did I have to use natural log, or could I have used any log at this step? I could use any log. Okay, so that's kind of, because of this power rule, and then dividing,
the change of base formula always works. Okay? So before we do some examples, I now want to talk about some mistakes I commonly see students use. I want to point out as many of these as possible because it happens a lot. Yeah, let's do something like this. Let me start with an example that's not logarithm based. X squared plus 9 equals 16. What is something you would do to both sides of this equation to get x by itself? Subtract 9 and then do what? Square root. Does anybody just want to square root now? Oh, this x plus 3 equals 4. Ning Ning, why are you saying no? Not allowed to do that, right? Essentially, I just did the square root of x squared plus 9, and I called that x plus 3. Does the square root of x squared plus 9 simplify? No. Do we have an exponent rule or a radical rule that lets me distribute exponents over addition or radicals over addition? No. I see that same type of mistake a lot when solving exponential equations. A lot of students will see an equation like this, and they'll be like, oh, let's take the log base 2 of everything. Take the log base 2 of that. Let's take the log base 2 of that. Let's take the log base 2 of that. And so this becomes 2x equals x plus 3. And hey, x equals 3. Okay? That's not good. You really royally messed up the right side of this equation. You could take the log base 2 of the entire left side, but do I have a log rule that lets me take the log of a sum and actually do something with it? No, you do not. Okay, that does not simplify, right? Here's another example. What's the log base 3 of 9? 2. What's the log base 3 of 27? What's the log base 3 of 9 plus 27? 2 point something, 3 point something. I don't know. Not 5, right? Not 5. You do not take the log base 3 of 9, log base 3 of 27, and then add them together. There's no log rule that lets you do that. And that is essentially what you did up here. You cannot take the log of individual terms. You can't. You can take the log of the whole thing, but not individual terms. Just like you can't square root individual terms. Just like you don't square individual terms. You FOIL it out. Okay? So we've got no way of simplifying this. Now, what is the log base 3 of 9 times 27? Try that without any sort of technology help. Is that? That is 5. Because what's the log base 3 of 9? 2. What's the log base 3 of 27? 3. And 2 plus 3 is 5. Even though I see multiplication, it turns into an addition. Right? We have a rule that we just learned that says that's the same thing as saying log base 3 of 9 plus the log base 3 of 27. That's 2 plus 3. The answer is 5. Okay? So make sure you know the rules, but also know what's not a rule. Here's another one. Simplify this down for me. What is the log base 9 of 18 divided by the log base 3 of 6? How does that simplify down? Anybody? It doesn't. That does not in any way, shape, or form simplify down. Isn't that hard to believe? Look at all those numbers. They're all 3s and 9s, but no, nothing. Nothing about that. You cannot cancel the 18 and the 6, the 9 and 3. We have no rule.
I'm laughing at the Snoop Dogg joke. You have to say it with bananas.
What?
Remember the Snoop Dogg joke?
Okay, why does Snoop Dogg need an umbrella? Faux drizzle. That's hilarious. Come on. Faux drizzle. You know, the funny thing is, she's like, you know what that means? That means that on school hours, she was on Facebook. That's where I posted that joke. All right. Busted. Okay. It's a plan. She can do whatever she wants. Now, how could you not laugh hysterically at that joke? That's a great joke. And it is Snoop Lion now. I know. He went to Jamaica, and now he's Snoop Lion. Now, what if we had this? What if it was the log base 9 of 18 divided by the log base 9 of 6? Does that simplify?
Yeah.
Yes. How does it simplify? That becomes, a lot of you are probably going to be surprised by this, that becomes the log base 6 of 18.
It's a change of base formula. It's a change of base formula only backwards. That's the only way it simplifies. If you try dividing that 18 by 6, you're wrong. It doesn't work. Because they're the same base, I can rewrite it as a new log using the change of base formula only backwards, right? But that's the only way it simplifies. A little bit surprising?
Okay. Here's another common mistake. I see this a lot. What is the log base 3 of x minus the log base 3 of y cubed? I want to condense that down to a single log expression. That becomes the log base 3 of x divided by y cubed. Right? I see a lot of students write that as log base 3 of x over the log base 3 of y cubed. Okay? That is not how the rule works. If that were the case, if this right here were the same thing as this, then 9 minus 2 is the same thing as 9 divided by 2. And last I checked, I don't think it is. Okay? So just be careful. I mean, try to be aware of not only what the rules are and being able to use them properly, but make sure you're also not doing things that actually there are not rules for. And it's tough knowing what are all of the infinitely many things I could do wrong. Don't do those. Right? It's hard. It's harder to know what you don't know than to know what you know. That was deep. That was good. I'm going to write that down, put it on a wall. That was good. Get erased. Oh, Mike. Sharpie on the Sharpie right onto the wall. Scotty, you get mad at me. Okay. There are two big things we like to do to practice these log rules, expanding and condensing. You better believe on Friday's quiz you're going to see some expanding problems just like this and some condensing problems, which hopefully we'll get to later. So let's expand 5x to the third y. So the log base 4 of 5x cubed y. Basically, you want to identify all of the things that you can possibly expand. Multiplications inside of a logarithm can be expanded. Divisions inside of a logarithm can be expanded. And exponents, powers, can be expanded. Agreed? Yeah. And you kind of want to do them in
backwards order of operations. So when I look at 5x cubed y, I see two multiplications, and I see an exponent. Now, typically, according to order of operations, which one do you do first? The exponent, then you do the leftmost multiplication, the 5 times, then you do the rightmost multiplication, the x cubed times. Well, you typically want to do them completely backwards. I'm going to break up the multiplications first, then I'm going to bring the exponent down. Again, a lot of students think that 3 is attached to the 5 as well, that 5 is not being raised to the third power, right?
Have I told you the story of my Italian professor in college? The pronunciation of sette versus sette? This is 5x cubed, not 5x cubed. Right? You hear the difference? No, it totally sounds different to me. Isn't that weird? This is 5x cubed, not 5x cubed. Right? Okay. Anyway. So first we break up all of these multiplications. We have the log base 4 of 5 plus the log base 4 of x cubed plus the log base 4 of y. That right there is the log base 4 of x cubed, not the log base 4 of x cubed. Right? See? Okay, now I think I'm confusing people. And then the last thing we do is we bring that 3 down. So we have the log base 4 of 5 plus 3 times the log base 4 of x plus the log base 4 of y. And that is as far as you can expand, and so that's where you would finish.
That is completely expanded.
So you always kind of go backwards order of operations. I have all these multiplications right there. I'm good to go. Now B is a little bit trickier, but not much. First of all, how many different operations do you see that we're going to be able to expand?
2. Out of the 4 total operations going on here, I'm only going to be able to expand on 2 of them. This division right here is going to become a what? Subtraction. And this radical is technically a what? An exponent. That's raised to the 1/2. And we'll be able to bring that down. See this multiplication right here? I'm not going to be able to expand that. I'll show you why. Let's first do the expansions we can do. And now, again, we go in backwards order of operations. The division is typically the thing you would do last, right? We're going to expand it first. Okay? Then we're going to do the radical.
So this becomes the natural log of the square root of 3x minus 5. I'm going to call that 3x minus 5 to the 1/2. Minus the natural log of 7. Then that 1/2 comes down. So we have 1/2 natural log 3x minus 5 minus the natural log of 7. So is everybody okay with us up to that point?
Now, why does this natural log 3x minus 5 not expand? Well, again, it's kind of like you have to go in backwards order of operations. According to order of operations, this multiplication and this subtraction, which one comes last? The subtraction. Do I have a rule that lets me expand across a subtraction inside the log? No. There's nothing I can do there. Does that make sense? Even though there's a multiplication, it doesn't come last. I can't do it.
Now, what if this was actually 3x minus 6, not 3x minus 5? I can factor a 3 out. Now, according to order of operations, what operation comes last? Now the multiplication comes last. By factoring that 3 out, I've changed order of operations. Instead of multiplying first, subtracting last, I'm now subtracting first, multiplying last. I can now expand across that multiplication if I wanted to. We could call this 1/2 natural log 3 plus 1/2 natural log x minus 2. Because this 1/2 is being multiplied by this whole thing. So if that whole thing splits into 2, both of them are being multiplied by that 1/2, so you have to distribute them. Does that make sense? So this is a little bit more complicated than you probably realize in Algebra 2, really thinking about all the order of operations. Then you also have some condensing problems, which is just going backward, taking an expression that's already expanded out and condensing it into one single logarithm. And that's all I got.
Oh my.